Okay, so today we will discuss a definition of subcategory functors between two categories, etc. Mm, so we'll see definition of the subcategory. So definition. A subcategory C of a category C prime, a subcategory C prime of the category C is a category. A subcategory itself is a category. A category such that first the objects of C prime are also objects of objects of C. So object class of objects of C prime is actually subclass of class of objects of C. Second, for objects x prime, y prime in C prime, this home prime, this home set that is uh, set of all morphisms from x prime to y prime in the category C prime is a subset of this home set C prime y prime. Three, if f prime is in home C prime x prime y prime and G prime is in home C prime x prime sorry, y prime z prime y prime z prime, then f prime compose G prime in C prime equals f in C, right? So because you see this f prime and G prime, they will be in markisms in C also. Hence, we can talk about f prime compose G prime in C. So this will be same as this one. So this is the definition of subcategory of a category. Now, a subcategory C prime of C is um, said to be said to be full subcategory. Full subcategory category said to be full subcategory if for all objects if for all objects x prime y prime in C prime home C prime x prime y prime equal to home C prime y prime. So set of all morphisms from x prime to y prime in C prime equals set of all morphisms from x prime to y prime in C, in the category C. Then we say that subcategory is a full subcategory. Uh, Now examples already so I will repeat. Already I discussed actually uh, the example 8, the the category in example 8, that is the category of finite sets and functions. Uh, Example 8 is a full subcategory, is a full subcategory of uh, the category in example 1. Similarly, the category of sets and injections, which is in example 5, the category in example 5 is a subcategory category of the category in example 1. It is not a full subcategory. You can verify this. Next, we discuss what is commutative diagram. So definition. A diagram of morphisms such as the square this set this square this is said to be commutative if any two compositions positions of morphisms in the diagram beginning at the same place and ending at the same place are equal, right? So for example, these two composed F composed H equal to G composed F prime. There are no such no other compositions, right? Which begin at same place and at same place. So this square is commutative if and only if F composed H equal to G composed F prime. Some categories which are associated to a given category. So given a category, see there is an associated category. There is an associated category called the category of morphisms of C. What are its objects? Its objects are morphisms and its morphisms. Its objects are morphisms uh, in the category C, and its morphisms with domain this morphism f from x to y and range in uh, f prime from x prime to y prime are pairs of morphisms g from x to x prime and so morphisms are pairs of morphisms g from x to x prime uh, and h from y to y prime such that the diagram this this is commutative. So in a similar way, we can get another category in which objects are diagrams of uh, morphisms in C, right? Uh, so we can continue like this. Next, we see definition of functors. So definition a covariant variant or a covariant or contravariant functor T from a category from a category C to another category D to another category D uh, consists of an object function which assigns assigns to every object x in C an object tx in uh, uh, D, and a morphism function which assigns every morphism from x to y in C to which assigns uh, to every morphism f from x to y a morphism uh, tf from tx to ty in D. So this is for the case of covariant functor, and for contravariant functor we'll have this in D, such that first T assigns identity morphism to identity morphism, and it respects composition T F G equal to T F T G, or so this is for the case of covariant functor, and for contravariant functor f g equal to t f t g. So this was the definition of covariant and contravariant functors. So some examples of functors. So first example, there is a covariant functor from the category of topological spaces and continuous function. Uh, category of category of topological spaces and continuous functions. Right? So there is a functor from here to the category of sets and functions. So category of sets and functions, which assigns to every topological space is its underlying set, right? So x goes to x by t, but here x is with it's a topology. Here means there is no topology on this set x, right? And this is called forgetful functor, right? So this is called topological space, and here with some topology, with topology tau x maybe x, this is underlying set of topology tau x. So this is called forgetful functor. This is called because it forgets some of the structure of a topological space, right? So it forgets, right? And it forgets the topological structure on x, and it gives the underlying set x only. Next example, so there is a covariant functor from the category of sets and functions to the category of R modules uh, and homomorphisms, which assigns to every set the free R module generated by it, right? So this is covariant functor, covariant category of sets and functions and T covariant functor. Here this is category of R modules and homomorphisms. R modules and homomorphisms. So here x goes to tx, but what is tx? It is the 3R module generated by x. 3R module generated by x. And because given any two sets x and y and function f from x to y, so you can see that here if x to y function is there, then tx to ty, we have tf, right? This. So this will generate a function from Tx to Ty. We call that Tf. So naturally, we'll get a homomorphism Tf from Tx to Ty. Next example, for any R module, M naught R module, this home not M, or you can consider home M naught, right? You can consider these two. This is a collection of set of all uh, homomorphisms from module homomorphisms from M naught to M for any given M naught is a fixed R module, and for any given R module M, this is a collection of all R module homomorphisms from M naught to M. This is collection of all module homomorphisms from M to M naught. So this is a home functor. This one is covariant, right? So what it does, it takes M, right? So here T equal to, you can write T equal to home M naught. So it takes this to home M naught. M. Similarly, if we consider this one, then that is this functor T prime, we can consider home. So it takes M to this one. So that will come out to be a contravariant functor. This is a covariant functor. Uh, from the category of R modules and homomorphism to itself. Uh, Next, we have, so this you verify with, uh, so this is an exercise. Covariant, contravariant functor. So verify means what can be the what it takes if you take a morphism f from m1 to m2, then what this functor takes, what kind of morphism it assigns to this morphism. Uh, you verify that, you try to see. Next, we have following theorem, which is very important. Uh, Let T be a functor from a category C to a category D, then T maps equivalences in C to equivalences says in D, right? Uh, this is very important. So proof is simple. Let F be an equivalence in C, then what we have, uh, I so take F, let F from X to I be an equivalence in C, then I T X, by definition of functor, this is nothing but T of Ix, and because F from X to I is an equivalence, we have this Ix is nothing but F composed F inverse, right? F is an equivalence means there is a morphism which is left as well as right inverse of F. So this is equal to, again by using property of functor, this is T F inverse composed T F. So this is for covariant functor. For contravariant functor, it will be T F composed T F inverse. It means what? It means that what we want to actually prove, we want to prove that if F is an equivalence, then TF is also is an equivalence. So this TF inverse is a left inverse of TF in D from here. Similarly, ITY equal to T. This is for covariant functor. Covariant functor. This is your TF composed T.